Okie dokie, welcome to FRQ number 2 for our E&M 2026 exam. So in this question, we have a thin, non-conducting charged rods S and T are held fixed in the XY plane as shown in figure 1. Rod S is oriented along the x-axis in the region negative 3L to negative L. Rod T is oriented along the y-axis in the region L to 3L. Each rod has uniform positive linear charge density of positive lambda, and point P is located at negative 2L, positive 2L. All right, in part A, we want to draw an arrow starting on the dot that indicates the direction of the net electric field EP at point P due to rods S and T. And then we want to do it for the origin due to the two rods, and then if I let go a negative charged sphere at the origin, which way would the acceleration be? Okay, so we're going to use some symmetry arguments for this one. So I'm going to look at rod S. So rod S, you'll notice that point P is exactly in the middle. So point P exactly in the middle above it. So if I think about, if I take like a little slicey slice, dq from my rod, and I think about which way that field is going to go, it's a positive charge density, so it's going to go up to the left from that little part. This little part is going to go up and to the right. So since I have the same amount of charge to the left as I do to the right, those horizontal components are going to cancel out. So my net field from rod S is going to be straight up. So my net field from rod S is going to be straight up. If I do the same thing with rod T, basically effectively just take this and rotate it to get rod T, he's going to feel that same force, that same field, to the left, okay? So from our symmetry arguments, we can figure out rod S is going to give me a component of the field up, rod T is going to give me a component of the field left. Since they have the same charge density, they have the same length, they're going to have the same magnitude of their respective electric fields. So this is going to be a nice little exactly at 45-degree angle up and to the left. Boom. Nice. Cool. All right, if we kind of do the same thing at the origin, if I have rod S again, and I take my little slicey slice of dq, the origin is directly to the right of it. So that's going to give me a field to the right, no matter where I am along the rod. So I'm going to get a component at the origin from S to the right. And if I kind of do the same thing with rod T is going to give me a field down. So it's going away from the rod, away from the rod. Same deal, that's going to be a nice 45-degree angle again. Now, they don't say anything about making the magnitudes, like the respective magnitudes of your arrows matter. So we're going to not care because they don't say to draw the magnitudes to scale. So, all right, so then for the acceleration, you need to remember that number one, if I'm a negatively charged particle, so positively charged particles are going to follow the electric field line. Negatively charged particles are going to do the opposite. So if I was going to put a positive charge at the origin, it would go down and to the right. But it's a negative charge, so it's going to do the opposite. So it's going to go up and to the left. Cool. That's part A. That was nice. All right, part B, we want to derive an expression for the magnitude E naught of the net electric field at the origin due to rods S and T in terms of L, lambda, and physical constant as appropriate. Begin your derivation by writing a fundamental physics principle, blah, blah, blah. All right, so we're looking for it at the origin. So we're looking at the situation where I have my rod, I have my origin over here, and we're negative 3L, negative L. So this is for rod S. Okay? Or we could also do T. So since we already said that S and T are going to have the same magnitude, just one's down, one's to the right, I'm only going to solve it for one and then use good old Pythagorean theorem at the end. So I'm actually going to do rod T just because it has positive numbers. So L to 3L. It's just a personal preference. Here's my origin. Okay, so I'm going to set it up. I'm going to have my little DQ. Here's my little DQ. Here's my little R vector coming down to the origin. Because remember, if I want to derive my electric field from scratch, that's going to be K, or 1 over 4 pi epsilon naught. I like K personally. And that's going to be K dq over R squared R hat. So in this case, dq, since we have a constant charge density, dq is my little charge density, my charge per length, times the little length. So my little length, right here, is a little slice of y. So it's going to be lambda dy. My r vector points from that little dq to the point I care about. So that's going to be, that distance is where am I on the y-axis, but down. So my r vector is going to be negative y in the y direction. So we'll go ahead and add our little j hats there. And then r hat is just j hat because it's in 1D, which is really nice. So that tells me that my electric field is going to be in the y direction, which is what we expected. So if we put that all together, we get K integral dq was lambda dy. My r squared is going to give me a y squared. Oops, that should be a dy, my bad. Boom, 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 boom. And then my r hat, negative j hat. So the negative j hat. Boom. Okay. Okay, so the limits of integration, remember we're integrating over the charge. So it's where is the charge? So it's going to be from L to 3L. So I'm going to take out my constants. So I have negative K lambda. We have our integral L to 3L of 1 over y squared dy. And that's going to be in the j hat direction when we're all done. I'm just going to drop that for now because we already decided it's going to be pointing down. So that's kind of just redundant at this point. All right, don't judge me, but if I'm integrating this, I still have to write it as that 30 years later. So if I'm going to add 1 and divide by the result to integrate, that's going to give me K lambda over y, flip the sign. So it's going to be positive L to 3L. Okie doke. If I plug in my limits, that's going to give me K lambda over 3L minus K lambda over L. Let's go ahead and take that K lambda out. 1 over 3L minus 1 over L. Let's get a common denominator there. Burm, burm, burm. So 1 over 3L minus 3 over 3L is going to give me K lambda. 1 minus 3 is a negative 2. So negative 2 over 3L. Cool. All right, so we're going to have a magnitude of 2/3 K lambda L pointing down. Cool. Alrighty. So then, with our j hat, sorry. So that negative sign actually came back to tell us that we're pointing in the negative direction. Nice. Okay, so remember from up here, we said that our origin was going to be pointing, at our origin, we're pointing down from rod T. We're pointing to the right from rod S. So I'm going to put those two together. So we figured out that rod T is going down with a magnitude of 2/3 K lambda over L. That means rod S is pointing right, also with a magnitude of 2/3 K lambda over L. If you remember your special right triangles from geometry once upon a time, that's a 45, 45, 90 triangle, which means that hypotenuse is going to be 2√2 over 3 K lambda over L. If you don't remember your special right triangles, then You can do Pythagorean theorem about it, and you'll get the same thing. Bam! All right, so 2 root 2 over 3, k lambda over L. That is our magnitude E naught for the net electric field at the origin due to rods S and T. Nice. Okay. Part C, rod T is removed. We just have rod S is then moved such that the right end of rod S is at the origin O. Rod S is then moved with speed v in the negative x direction as shown in figure 3. On the axes shown in figure 4, sketch a graph of the electric potential V naught at the origin due to rod S as a function of the distance r between the origin and the right end of rod S. Okay, now for this one, we could derive an expression for the electric potential, but we could also use some logic, right? So I know that when this rod is touching the origin, because remember, potential goes like kq over r if I'm talking about a single point. So if I have this little slice of dq right on top of the origin, I'm getting a big potential because my r is 0. So I'm going to have a really strong potential. Also, it's a positive charge, so it's going to be a positive potential. And then as that rod gets further and further and further away, eventually it's going to get so far away that it's going to go to 0 because it goes like 1 over r. So this should be a nice concave up asymptote down towards 0. That is a horrific looking curve, but you get my drift. So it's going to be concave up. So your points are probably going to be it's concave up and it asymptotically approaches 0. And then you're going to have a very strong potential over here. So it's going to kind of go asymptotically up towards the y-axis. So it's just a sketch. We don't care about specific values. We don't care about specific functional dependence. Because once this rod gets really, really, really far away, it's going to eventually look like a point once it's super far away. So it's still going to have that kind of 1 over r look. If you actually derive it out, it ends up being a natural log, like an upside down natural log, but it's still going to have that concave up asymptotic behavior. So you could derive it, but we don't have to. We know it's going to be asymptotic at 0, and it's going to be really strong at the origin. So that's all we're going to do. We're not going to derive it because I don't want to. It's a waste of time. Cool. Part D. A new thin, non-conducting charged rod W has the same length as rod S. Rod W has a uniform negative linear charge density and is oriented along the y-axis. Rods S and W are initially held fixed with one end at the origin. Starting at the same time, rod S is moved with the speed v in the negative x direction, and rod W is moved with the speed v in the positive y direction, as shown in figure 5. Indicate how the sketch of v naught at the origin due to both rods S and W as a function of r would be different from the sketch made in part C. Okay, so this one you need to remember that potential is a scalar. So potential is a scalar. Since rod S and W are the same length, they're the same length, they have the same lambda but opposite signs, and they're going to be the same distance away from the origin at any given time. So same distance from origin at any given time. So that means they're going to have the same value of the potential, just one positive, one negative. So same V, but opposite signs. And since potential is a scalar, that means we literally add them together. So if I have positive 2 volts and a negative 2 volts, I get 0. So that graph, they're going to cancel each other out the entire time. So that graph is going to be a nice horizontal line at 0. Meow. So it's going to be 0 the whole time. So v equals 0 forever, because they're going to cancel each other out. Because all things being equal except opposite signs. No more. The end. All right, cool. So parts C and D you actually didn't have to do much math for. You could logic your way through them, which I think was kind of the point, is why they put that whole velocity part in there, to kind of get you to be like, what? Because I feel like some people probably saw that velocity and then wanted to start doing some like r as a function of t, and no, you don't have to do that. You don't have to do that. It's effectively the same thing as if your rod was stuck and you're just trying to figure out what's your potential a distance r away, where r is a function, okay? So not that deep.